You ready, Gary? Okay. Let me have your attention. Let's begin. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Mr. Mike Soulard, who is the Manager of Customer Relations for AECL Technologies Development, which is the Atomic Energy of Canada Limited. Mike received an MS in Mechanical Engineering from the University of Toronto in 1980. He received an MBA, also from the University of Toronto in 1985. He has been with AECL since 1980, 23 years. He's had a variety of responsibilities. His most recent responsibility is with the ACR, that's the Advanced CANDU Reactor Business Development Unit, which is the subject of today's presentation, which is entitled Advanced CANDU Reactor Competitive Design for the Nuclear Renaissance. Mike, welcome.
Thank you, Professor Dodds. Thank you. It's a pleasure to have the opportunity to talk to you today. As you can see, I have a ubiquitous title, Customer Relations. I'm part of a group that really is the technical liaison between our engineering development group back in Canada and the U.S. utilities and the nuclear reactor staff that we deal with. I work for our the ACL subsidiary we have in the U.S. We have two offices in Maryland, one in Gaithersburg and one in Frederick. And I work out of Frederick in our U.S. licensing project office. So today I'd like to talk to you about our Advanced CANDU Reactor. And for those who may have gone and perused the NRC website, you probably will be aware that we're in a pre-application phase right now. We've had several meetings with the NRC, and of course any meeting you have with the NRC is in public knowledge, so there's probably a lot of material there that if you're interested you can certainly peruse. I'm going to give you a very quick overview, obviously, of the ACR, covering some obviously technical features and some business development features and licensing features. I'll start off with a very quick overview of CANDU reactors. CANDU is an acronym. The CAN reflects Canada. The D stands for deuterium, which represents our heavy water, and the U represents uranium. I'll talk a bit of the design features that make up the ACR product. I'll give you a bit of the status of our design program. It's underway, and I'll give you some information on the time frame. Certainly, if we're going to build a new reactor in North America, one of the things we have to do is meet a very short project schedule, in particular construction schedule, and stick to it. So I'll talk a bit about some of the design features that we've implemented into the ACR to help us achieve these challenging schedules. I'll tell you a few things on the balance of plant development and the status of where we are in business development, with a particular emphasis on our licensing activities with the US NRC. And then I'll close off with some general subjects. I should have turned off this. Anyways, CANDU reactors have been licensed and built around the world. We're operating in, I guess, 4 countries. The first 700 megawatt class started in the 1970s. Really, the early 70s class was really a 550 megawatt. Those are the Pickering reactors. In Ontario Hydro, we have 500 megawatt class, and we have a 900 megawatt class reactors, the Bruce and Darlington reactors. ACL has also designed a 700 megawatt class called the CANDU 6, which we developed in the 1970s and been selling since then. And I'm fibbing right now. We don't have 8 CANDU 6 reactors operating in four countries. We actually have 9. One went into service just last month, I believe, or maybe in February, in China. And so therefore, we have 2 CANDU 6 reactors that are under construction. Now, obviously, the CANDU 6 is the design basis that led us to the new ACR design product. and I'll say a few words about it. I'll tell you a bit about what we've been doing in the past 5 or 6 years. I guess in the past 6 years, we've built 5 reactors. The most recent ones are in Qinsan, it's about 60 miles south of Shanghai. There are 2 700-megawatt plants. One went into in-service in February, I believe, maybe a bit sooner than that. The second one's going to go in service in November 2003. Cernavoda 2 in Romania is under construction. We have 4 reactors in South Korea. The first one was built in the 1980s. The most recent ones, Wolsong 2, 3, and 4, were built in 97 to 99 respectively. So we have a lot of experience of actually building reactors very recently and, as we speak. So we have a significant so-called project and construction experience that we want to feed off and improve upon in the ACR development. CANDU performance, in terms of the CANDU 6, I guess the lifetime capacity factor has been about 88%. We've learned the same lessons, or still learning the same lessons that the U.S. plants have learned in the 1980s and 99 about operations and maintenance, and you got to pay attention to it. And Canada is been a bit behind in learning these lessons, but is actually implementing it. And so we've seen recently all the benefits that you've actually realized in the United States. We have these reactors that are operated by many diverse countries. We have the Chinese, we have the Romanians, we have one in Argentina, and the Koreans. And they've been able to operate these quite successfully, some with very high capacity factors, as you see here. The Korean units tend to be operating at quite high capacity factors. In 2001 and 2002, the top 3 CANDU 6 units were in Korea, and they've had an average capacity factor of about 96.6%, 6.6% in both years. Most of these countries that we've sold our CANDU 6 have a PWR base. I mean, they tend to have or are operating PWR type reactors, and they tend to follow the U.S. experience with PWR reactors, and they've been able to apply that knowledge to operate a different technology in some ways and achieve very good performance. And certainly with our ACR, with the new ACR product, we hope, not only hope, but we intend to improve upon what we've learned in CANDU 6 and actually do a lot better things to ensure that we have an extremely high performance target. It's one of the important things that will help us make a new nuclear build an achievable target over the next 10 years. Most of the utilities want the plants to be built on time and on schedule and to be operated with minimal problems at a high capacity factor. And there's been a lot of work done in the world to try to achieve that. So why did we develop an ACR? Well, certainly I think us, including the various competitors such as Westinghouse and so forth, we looked at the emerging market in the late 90s. Electrical markets were getting deregulated, and it's very important that nuclear had to be competitive with natural gas and coal. And it was very important that we really focused on some of the key economic targets, such as capital cost, O&M, and project schedule. And so we asked ourselves internally, what can we do with our existing design? How can we change it? And we'd be able to achieve those targets. Obviously, the answer to that was yes, otherwise I wouldn't be here. But so let me give you a bit of the background on that. With respect to the economic basis, well, the way we develop CANDU is we've taken an incremental approach to developing the CANDU product. It's evolutionary in principle. In other words, we understand where we've been. We'll push the product a bit more, qualify it, get experience for more, and then incrementally improve the product. So CANDU 6 technology is a well-known technology to us, and we want to make sure we didn't extrapolate too far, and thereby introduce technical risk that would be very hard to quantify. So the ACR is based on what we consider to be a proven in service CANDU 6 technology. As I mentioned, we have a lot of experience building reactors. Our projects, believe it or not, have been built to cost and schedule, and I'll show you some data in a little while. AECL tends to offer turnkey solutions, and in China we were the prime contractor. We worked with local Chinese construction companies and procurement companies, and we had Bechtel on the balance of plant, and a very complicated relationship there, but turned out to be very successful, and they were built ahead of schedule. And we have a very solid cost and delivery basis. Our procurement supply chain is well known. We know where our equipment is built, who we can go to. And so that's very important if you want to be able to respond to the emerging market over the next 5-6 years. So that's another thing. In our design, we want to make sure that we took advantage of the experience we've had in the past 5 years, and then just, maybe jump it ahead a bit. And of course, we want to be economically competitive. And as I'll show you, we want to, the capital cost and O&M and the schedule were the three cost targets that we want to make sure we could achieve, and that imposed certain design implications on the ACR. The CANDU fuel, as I'll mention, tends to be a low cost, has a low fuel cost. With online refueling, and the bundles are cheap to manufacture, the fuel cost is a small component of the overall levelized unit energy cost. So that's one advantage that we tend to try to take advantage of. Here are some of the key economic requirements. Obviously, on capital costs, we're trying to make sure that the plant can be built at $1,000 on it per kilowatt. So for a 2-unit, 700 megawatt plant, that would be $1.4 billion. As far as the unit, the LUEC, we're looking at $28 to $32 per megawatt hour. On O&M and fuel costs, less than $10 per megawatt hour. The project schedule, and by that I refer to from the contract effective date to the in-service date, is 48 months. And of that 48 months, we're talking about construction. When we first start pouring concrete and turn it over to fuel load, is 36 months. And that, if you have any knowledge of typical construction periods in the nuclear industry, is very challenging. We're looking at a lifetime capacity factor of 93%, and the plant should be able to operate for 60 years. And so, although hidden behind there are a lot of design issues that you have to tackle head on, and I'll cover a bit of them to give you a flavor of how we dealt with it.
Those are targets, they're not experience.
We've never built one, right? We've never built an ACR, right? No. So therefore, obviously then, to maybe a jaded audience, you have to convince them, why do we believe we can get there? Well, here's a slide, it's a summary slide that sort of gives you a reason why we can. The CANDU, the CANDU 6 overnight capital cost was $16.40 per kilowatt. We know that. We just built 5 in the past, or 6 in the past 5 years, or was it 5 in the past 6 years. We know our database. Now, we've done certain things in the ACR. We've removed the heavy water out of the reactor coolant system and all the associated heavy water systems on the primary side. And there's been other systems. Sure. Yes, I'll get there in a second, yeah. So, and we reduced some other systems. Now, heavy water is like gold. It's an expensive product. And to remove all the systems associated with it and other things, we were able to reduce by about $120. The ACR core is much smaller. As you will see, it's significantly smaller than the CANDU 6 core. So it's a smaller core, then the equipment's smaller, and if the equipment's smaller, it costs cheaper, to be simplistic. And so our calculations show that we're going to get $90 out of that. We've done some plant optimization, or I should say our partner Hitachi has done some plant optimization on the TG side, on the turbine side, higher efficiency. We're working at higher pressures and temperatures, and that'll recoup us $50. We've gone a long way to try to standardize our components. I mean, there's a lot of valves in a nuclear plant. We try to make sure we don't buy 35,000 different varieties of valves. We try to stick on a few key types of valves, for example, try to standardize our hanger design, so on and so forth. And that gives us a significant cost reduction. For the past 10 years, we've been doing a lot of work in advanced construction technologies, how you build a reactor quicker and faster. And I'll touch base on that during the talk, but that gives you a significant cost reduction, such that when you do some simple math, you come to your $1,000 per kilowatt. And this was the initial, when we looked at it on a conceptual level, this was what galvanized us and said, okay, we can do it. And of course, in the past 4 years, we've been doing the details to back this up. So this is an ACR that's sort of outside here in the Blue Ridge Mountains. And I'm hoping. It's a 2-unit plant. It's an integrated plant. And, oh yes, that's right. Each unit has a nominal gross output of 731 megawatt electrical. After taking away the house load, the actual production is 681 megawatt electrical, the net output. Now, a CANDU and a PWR, really in large part, if you look at it, they're quite similar. I mean, the balance of plant is a balance of plant, There's nothing strange about whether it's CANDU or a PWR. Turbines, a bunch of heat exchangers, feed water, condensers, so on and so forth. The big difference is the core. Obviously, oops, what did I do? Okay. The PWR, you're familiar with the pressure vessel. Our pressure vessel, so to speak, is a cylinder on its side with a matrix of tubes traversing it, which I'll give you better pictures later on. That's where the big difference is. And there are a few other things, maybe on some of our components on the safety shutdown systems. But in large part, about 75% are very similar to a PWR. So it's not as if this is a strange animal. Certainly the core is different. And this is a picture of the core, what we call a calandria and shield tank assembly. You have the calandria, which is the outer diameter of the green area. That's filled with moderator, low pressure, low temperature moderator to slow down the neutrons. We're looking at head-on all those little tubes are what we call pressure tubes that traverse the core longitudinally, and the bundles are located in each of those tubes. In an ACR, there's 284 channels. In a CANDU 6, there's 380. Our reactor coolant system is filled with light water. It used to be heavy water. We removed the heavy water. Now it's light water. We have a shield tank surrounding the moderator, which is filled with light water, and that provides a backup heat sink. Our mechanical control absorbers and shutdown SDS-1 shut-off rods and mechanical control units are positioned at the top of the reactivity deck, and they're inserted in these thimbles that enter the low-pressure moderator. They do not traverse the high-pressure reactor coolant system boundary, such as you would find in a PWR. And so they're gravity-driven. Upon a signal, the clutch releases and it drops. Our safety shutdown system 2 is a pressure injection gadolinium poison into the moderator, which mixes in the moderator and stops the fission process. Both of these shutdown systems are fast-acting, and they shut down the core within 2 seconds. 2 milliseconds, sorry. What else can I say here? This is the side. I showed you the front. This is the side view. So this is the channel, and we have 284. And there's bidirectional flow. So when you look at the matrix, one channel the flow will be going away from you. Step aside to the next channel, the flow is coming towards you, so on and so forth. Each channel has 12 bundles, and those are the bundles in here. The reactor coolant will come in through the feeder pipe flow down the annulus through the bundles and out, back up the pipe into the steam generator and from the steam generator to the heat transport pump or the reactor coolant system pump and back and around. It's a figure of 8 loop. Each pressure tube is surrounded by a calandria tube. The annulus between the pressure tube and the calandria tube is a low pressure gas, and that's just to detect if there's any fission products in there. And the calandria tube is the boundary between the moderator and the pressure tube. There's a high pressure inside the pressure tube, and there's a much lower pressure on the outside of the calandria tube. The basis of the ACR design, I mentioned, it's evolutionary approach. We want to build on CANDU 6 and not extrapolate well beyond what we already know. What have we retained from our traditional CANDU 6 features? Well, we still have our modular horizontal fuel channels. What do you mean by modular? From 2 respects. You can change the output of the reactor from a design point of view by just changing the number of channels. Now, obviously, you don't do this on an online basis. I'm talking about it. We're working on ACR 1000. The way we go from an ACR 700 to an ACR 1000 is just by adding more channels. Depending on how many more channels you add, sometimes it will force you to increase the pore size. Modular, from the point of view, you can replace these also very easily, for whatever reason. We've retained our simple fuel bundle design, which I will show you shortly. We still retain our cool, low temperature, low pressure, heavy water moderator. We have high neutron efficiency. Our burn up for our CANDU fuel, our ACR fuel, is 20,000 megawatt per ton, electrical per ton. We have on-power refueling. We have a 2-bundle shift. In other words, typically in the CANDU, in the ACR, you will fuel maybe 3 to 4 channels each day. Each refueling, the machine will come and add 2 fresh bundles in at the inlet end, and push out 2 old bundles from a burn-up point of view at the back end. And it's bidirectional fuel. We have 2 machines on each side of the fuel channel. We have a passive shutdown system in the low-pressure moderator. It's a heat sink. And we also have a light water shield tank as another backup heat sink for severe core damage. Some of the innovations or design features that we've introduced from a safety perspective or for a cost optimization perspective are the following. We've developed a new fuel bundle. It's called the CanFlex fuel bundle. I have a slide on that later on. I'll show you. We now have slightly enriched uranium. CANDU 6 is where we're with natural uranium. Now we've gone to a slightly enriched uranium, about 2% slightly enriched uranium. PWRs are typically 4 to 5% enrichment. We have improved core characteristics. What does that mean? We have a very high radial form factor, so the power profile across the core, if you look at the core, is very flat. What does that mean? Basically, each channel has about the same power. If you're familiar with in a CANDU 6, the channel power would reduce as you went towards the outside of the core. Oops, pardon me. We've gone to light water in the reactor as a reactor coolant. Our plant arrangement has been optimized. We try to get a very small footprint so that we can footprints are at a high premium, especially in countries such as Korea, China, and so on and so forth. And so you want to try to optimize the size of your overall plant, and we've done that. We have a reserve water system. It's a passive water system. I have a slide to show you on that, which is back up to the steam generators in case of a loss of feed water. We've achieved higher thermal efficiency by increasing our temperatures and pressures. We've gone from 10 MPa, which is, I guess, 1450 psi, to 12 MPa, which is, my units are correct, 1480 psi on the primary side. That corresponds to saturation temperature of 310 C to 325 C, which is, I guess, in Fahrenheit is 590 to 615 Fahrenheit. On the secondary side, we've gone from 680 psi to 705 psi, which corresponds to temperatures of 258 to, from 500 to 534. So we've moved up higher temperatures and pressures, and we've been able to go from a thermal efficiency of about 34% up to 37%. And talk about overall plant efficiency. And we have a very much smaller reactor core size. Our typical core size was 7.6 meters in CANDU 6. In an ACR, we've gone down to 5.2 meters. A meter is about a yard. I'm not sure how familiar you are with SI units. I apologize if I...
You do not have to convert.
Okay, good. I won't.
Colin, you like it?
That's not very serious.
Before, in the previous slide, we saw the front view of the Kalenian shield tank, and this is sort of a side view. It's very similar to design to our 900 megawatt class reactor in Ontario, the so-called Bruce and Darlington Kalenian shield tank, except it's much smaller. In fact, the core size of that is I think it's about 9 meters, if I recall, and now we're down to 5.2. So we've made everything a bit smaller. So obviously there are some what I would call space allocation challenges. How do you make things and how do you fit things into smaller spaces? And that's one of the challenges we have, and that's what we're working to. And obviously we feel we can do it, but it's not the physics that's complicated. It's really the mechanical thing, the mechanical space allocation that is really the complex engineering feat that we have to tackle on here. The physics is simple, whether you go big or small. It's neither here nor there. This is a view of a fuel bundle. It's 1.625 feet, about 4 inches in diameter, weighs about 50 pounds. The CANDU 6 bundle had 37 of these pins. In ACR, we're using what we call our CANFlex bundle, which has 43 pins. There are two sizes. The inner pin and the next six pins in the inner ring are 13.5 millimeters in diameter, outside diameter. The other, is that right? Yes, that's right. The other 35 outer pins are 11.5 millimeters in diameter. The center ring is filled with natural uranium and a bit of dysprosium. We put in dysprosium because to achieve our negative void coolant reactivity. People are familiar with CANDU 6. We've always been criticized for having a slightly positive void reactivity. In the ACR, all our reactivity coefficients, void, temperature, and so on, are all negative. The other 42 elements are filled with a 2% slightly enriched uranium, U-235. The time average bundle power, for physicists, I'll give you these numbers, is about 910 kilowatts. The time average channel power, in other words, each channel on a time average basis would have 7.3 megawatts. Instantaneous power would be 7.8 megawatts. The CANFlex bundle 43 element has allowed us to go to much lower linear element ratings. We've gone from, if I recall, something like 63 kilowatts per meter to 51 kilowatts per meter. So from a safety analysis point of view, these are all good things. So that's our bundle, and you put 12 of these into a channel. They look like look like one of your own fuel assemblies, except yours are vertical, ours are sort of horizontal. So this is our ACR plant layout. You have the reactor building. It's a 2-unit plant layout. Reactor building in the middle. You have the reactor auxiliary building, which is a multi-story building surrounding it, each of the reactor buildings. All the nuclear and safety support systems are in those two buildings. The 2 units share common services in the maintenance and service buildings, and they also share a control room. So in the maintenance and service buildings, you'll have your rad waste facilities, your fuel handling facilities, and so on and so forth. We have a secondary control unit out here, which is also seismically qualified, Each of the units have two diesel generators supporting it. They're located on the side here. Obviously, this is our turbine building. You'll find the turbine in there. And our switch yard is on the opposite side. The AAB exclusionary area boundary is 500 meters around the center of each reactor building. Our ACR reserve water system is a passive system. We have a tank of water, sort of like a donut, at the top of the reactor building that is gravity driven. It will provide a feed to the steam generators in case of a total loss of the main feed water system. It also serves as a backup to our long-term cooling system. And as it says there, it's also a backup to the moderator and shield tank in case of severe accidents. Status of the ACR design. The conceptual studies began in 98, something like that, 1998. They were basically completed in March 2001. Since then, we've been doing the detailed engineering, and we so-called define our reference ACR 700 design. That was completed in March 2002, at which time that we felt we met all our safety, cost, and schedule targets. And we've also been considering a different size, the ACR 1000, but the level of work on that size is less than on the 700 right now. Our full attention is on the 700. The engineering program is a 4-year program, starting January 2002 to be completed in September 2005. Well, it's a 45-month program actually, to do all the generic engineering, and to have it ready to offer to the market and to support all our pre-project licensing. We've already started our Canadian licensing, which we hope to finish by 2004, end of 2004. As I said, we are already in a pre-application phase with the US NRC. We launched that in, I believe, in June or July 2002. We intend to submit a design certification to the NRC in September 2004. And we currently, as far as the engineering staff, we have about 160 people working on the nuclear steam supply side, NSLS, and we also have some people in Chalk River doing the specific R&D support to back up our design. We also work with partners. We have some partnerships with Hitachi, who are working with us Hitachi is focusing on the balance of plant design and also doing a lot of work on the TG set. And we're also working with different AEs, an AE in Canada and an AE in the US, an architect engineering firm. So I'm going to skip the introduction of all these people. Suffice to say that I'm there. But anyways, we have 160 people in our Mississauga offices outside Toronto, and another 20 to 30 who are directly involved on the R&D side up at Chalk River in our laboratories north of Ottawa. Now, if we're ever going to build another reactor in North America, we can't have the same sins that we had in the 70s and 80s. We've got to make sure that these things are built on time and on budget. And so, and most numbers, the target that are sort of talked about in the nuclear renaissance field, so to speak, is this 36-month schedule. And so I'll talk to you a bit about sort of the design features that we've implemented and that give us confidence that we can achieve this. Two important aspects are modularization and open-top construction. In the past 10 years, as we've been building our CANDU 6 reactors in the various countries, we've been doing a lot of R&D development on advanced construction techniques and construction materials. And we've been incrementally introducing them as we've been building each successive plant. And certainly open-top construction is a very important method that allows you to really shorten the sequences. Typically, when you build, certainly in a CANDU reactor, you would construct, you would introduce all the material through the door, side door, and you would build up from the bottom up. Very time consuming. Being able to take and lower equipment from the top has been able to really significantly reduce the construction. And here's an example. In the CANDU 6, we had a dousing system, a very complicated system at the top of the reactor building. Typically took 6 months to build that because the people would have to be up there in scaffolds and do all the welding and bolt tightening and so on and so forth. And it was on the critical path. Now, the dousing system, like in Chinsan, was built off on the side, not on the critical path, and built in modules. In fact, the dousing system is a circle, so to speak, and they were built in 6 pie wedges. And what you see here is one pie wedge being lifted, dropped in, soldered in. And that whole thing, installing it, took 2 weeks. The 6 months, the building on the side is immaterial. It was done on the side, it's on the critical path. As long as the material came to the site, hooray. And so this is the type of things that we're trying to introduce in ACR, is taking advantage of modularization, which is like plug and play, and dropping it into the reactor from the top, and facilitating a faster sequence. These very heavy lift cranes are very powerful. I mean, they can lift up like 700 tons. So they're impressive to see when you go to a site. You don't want to stand underneath them though when they're lifting something. But now modules, most of the new designs that are being offered, in the world right now, they're incorporating some aspect of modularization. And to be crude, it's like a plug and play. Try to build a subset of some process system, equipment, whatever, with all the associated electrical instrumentation. Build it off on the side, build it in the factory, whatever. As long as it arrives at the plant at the appropriate time, then you hook it up to the crane and then drop it in, and then plug and play. In CANDU 6, it was never designed with modularization in mind. But as we've gone down the past several years in building it, we've tried to introduce modularization concepts where we could. And in Wolsong, we were able to introduce 6 modules. For Chinsan, our project in China, the first 2 units, we introduced 15. In Chinsan, we built the project ahead of schedule. And there are discussions to do a repeat, the so-called CANDU 6 repeat. And we've seen further opportunities. And the feedback from the construction people, they come up with great ideas. They say, gee, you should be doing this. And in fact, their ideas are so great that we know for a CANDU 6 design, we can go up to 34 modules, which would help us even cut down further on the project schedule, as I'll show you in a few minutes. For ACR, to date, we have 105 modules, and that's in the reactor building. And this is an example of a module. It's a module that consists of the moderator pump, heat exchanger, the associated piping and instrumentation. And you see some size here, 11 meters by 6 by 6, about 45 tons. That you can build it in a factory on the side, have it shipped over, and you drop it into the reactor building. It saves on construction costs. That's what you're trying to avoid, having a construction delays, which with interest costs drives the price through the roof. If you look at from the top down, our reactor building, we've divided into what we call construction compartments, or for lack of a better word, silos. And we want to drop the equipment into each of these silos. And each of these silos you can think of it as a mini project. They're independent from each other. We can be working on installing all the equipment in this silo, DA1 for example, and working from the top down, and not have to worry about this silo. We can leave that empty until such time as it's required to bring the equipment. So what you have here, I think you have maybe, 10, 11 silos. They're all sort of like 10, 11 little mini projects. So that facilitates a fast construction sequence, as long as all the interfaces between the silos are done properly. In other words, you have the proper instrumentation, piping connections, and then at the end of the day, you just sort of, tighten the bolt, so to speak. And so in the ACR, we've taken this to the, I'm going to say to the extreme, but we've developed that to a large extent, and that's one of the ways we're going to try to achieve our construction schedule. Here's a bit of a rationale why we think we can achieve it. In Chinsan, we are able to do the construction in 47 months. This is the total. The total project was 72 months from contract effective date. The first 17 months were site preparation. Then you did the first concrete. You had fuel load here, and then you had the commissioning. But we were able to actually achieve a 47-month schedule. I think the contract said something like 50. I can't remember. I think it was a 2 to 3 month savings. On CANDU 6 repeat, given the lessons learned and the new modules we're going to introduce, we're ready to sign a contract, for example, the Chinese, for 42 months. Now that's for CANDU 6. The ACR is built with modularization in mind, built with, to facilitate construction, the construction schedule. Our first pair of units, what we call the first unit, is a 40-month schedule. By the third pair, so reactors 5 and 6, we believe we can get that down to 36 months. Obviously, for the first pair, you got to work out the bugs, right? There's the whole issues of the supply chain of modules to the site and the lessons learned and all that. But given our experience with CANDU 6, we believe these are conservative estimates, and we feel we can achieve that. So when we talk to various utilities, this is the message we're telling them. We can build it in 40 months, and then by the third pair by 36 months. Now, that doesn't have to be the same utility. That's any pair, the third pair anywhere. And this is sort of a bit more detail on why we believe we can go from 47 down to 36 months. On some of the benefits we can obtain from the civil construction of the reactor building, the open top installation, the modularization aspects, some of the advanced technology tools. A lot of that has to do with configuration management and the whole paperwork, right? It's all like, in Chinsan it was all electronic, but there's still room to improve. It becomes very difficult when changes are done at site and you got to feed that back to engineering. In the old days when you had paper copies, that was a tremendous headache. And so there's a lot of, in trying to use electronic tools right across the design, construction, procurement, post-construction, commissioning, feedback, you can really recoup a lot of savings. And that's why we believe that going from shaving off, I guess, 9 months or 11 months, I should say, is entirely possible. And this is just a high-level summary of a lot more details. The balance of plant, again, Hitachi is working with us. They're partnering with ACR. They're doing all the modularization of the balance of plant and also providing the TG set. And the TG set will give us about 37% thermal efficiency. And so, I mean, it's a tight team because we can't work separately. I mean, the balance of plant and the nuclear island have to talk to each other very, very closely. On the business development side, in the U.S., we started our pre-application in June. It's going to be completed in 2004. We're going to submit the design certification in September. We actually launched the product in the United States, as I said, in June. 3 utilities who are doing their early site permit applications have included the ACR as one of the 5 reactor designs in the submission. We had a utility supplier workshop in the States, in Charlottesville, in October. We had a constructability workshop with the utilities held in February. And we typically have 1 or 2 workshops every year. We also, at one point, worked closely with British Energy in the UK and Bruce Power, that was owned by British Energy at that time, doing a feasibility study to replace all their AGRs. There's 8 AGRs in the States, in the United Kingdom, that are coming to the end of their life and have to be replaced sometime about 2010, 2015. we completed a feasibility study, positive conclusions, but then if you're familiar with what's happened with the British Energy and the whole UK market, that's come to a bit of a grinding halt.
Comment on that.
Pardon me?
Comment on that, if you would.
Well, the way they deregulated the market in the UK was not very favorable to the nukes. Okay, they had high cost producing units, and they just couldn't make any money, and it drove them to bankruptcy. British Energy basically was bankrupt until the UK government then provided some loans to them to continue operations. They had a white paper recently. There's the so-called UK government white paper on energy, where they did not come out very strongly in favor of what I call real support of the nuclear industry, as opposed to your energy policy that's been recently tabled. I guess in your House of not going to say House of Commons, but House of Representatives. Sorry. And anyway, so the British Energy, they have to replace the power. There's no doubt about it. They're going to suffer shortages. They can replace it with windmills, chickens, whatever they want, but they have to replace it. Right now, the government hasn't been willing to take a stand on it. And so our discussions with British Energy are in just in standby. In Canada, pre-licensing is under, and we're actively working with Canadian sites, in particular working with Bruce Power, which was formerly owned by British Energy, but has now they were bought out by Cameco, which is a uranium supplier to not only Canadian reactors, but to the U.S. industry in the world. In summary, well, we feel that ACR is built on a solid basis that we have in CANDU 6. We've introduced some enhanced safety features. We believe the economics are good. We think we can achieve those targets. I outlaid the capital costs and schedule targets. Licensing activities are underway, and we're trying to pursue this aggressively. And so far, our experience with the NRC has been really great. It's going well, and go take a look at the website, and you'll probably see a lot of material there, more material than I presented here. The pre-application, let me just say a word about pre-application. We've identified more or less 12 topics that we consider to be, to use maybe a crude term, showstoppers. And I'll give you a couple of examples. Our pressure tubes are made with zirconium and niobium, and that is not an ASME material. But we have 50 years worth of research we understand that material, so it's a discussion with the NRC to say that is that acceptable. We also have 50 years worth of, our Chalk River has been operating since the Second World War at the start of the Manhattan Project, so we have a lot of R&D in all aspects of CANDU design. So we have to make sure we don't want to repeat that, because we're not going to spend tons of money to repeat all that research. There maybe have to be some aspects of that have to be repeated, what we call complementary R&D, to make sure that the NRC is convinced that that there's a firm footing on some of the key issues, and that's acceptable. But we're not going to redo 50 years. So we've identified these 12 topics, and at the end of the pre-application phase, we're hoping to get from the NRC that says, hey, everything's cool, showstoppers, looks good, please proceed. And then we'll go into the design certification phase. Design certification phase is very intense, very expensive. So it's about a 5 to 6 to 1 cost ratio between doing a design certification and the pre-app phase. In the pre-app phase, you familiarize an NRC, and you deal with some of those 12 topics. In the design certification phase, you do the whole enchilada, and it's the whole design in detail. And so we have our engineering and R&D teams mobilized, and we have partners involved, and utilities in North America, both U.S. and Canadian, are interested, and we're working and engaging them as best as we can, and pretty exciting these days. And hopefully we can have a unit built and in service by about 2012. Thank you.
Time for questions and comments. Mario?
Right. One of the issues I understood was on the typing and seismic issues. Is that one of your 12 showstopper issues? Or is that?
Oh, you're talking about the containment design?
Right. The pressure tubes present some seismic.
Well, the pressure tube is a material issue, which is one of the so-called 12 showstoppers. I don't like that word showstopper, but our containment design is also different in Canada than in the U.S. And so we've been looking at the standard review plan, which is the basis for the design certification. We've been going through all those requirements and making a decision internally and saying which ones will we just adopt and not fight the fight, so to speak, and which ones can we say, no, our Canadian design meets the intent and is basically the same, and let's just engage the NRC to convince them that. And which ones will we really, stand our ground and not budge? And so that whole process is underway right now. And on the containment design one, that's still being debated on exactly the approach that we're taking. I mean, I don't want to say too much because that's an ongoing discussion right now. I'm not the licensing manager, and he'll wrap my knuckles, but.
Okay. Other questions? Julie?
Is the digital instrumentation included in your ACR design?
Digital instrumentation.
Yes. And we're using the distributed control systems in the ACR design, and even more. I mean, CANDU 6 is digital control, and we're doing even more in an ACR.
How will you license in the United States?
How will we license this in the United States? That's one of the topics we'll be discussing with the NRC. We're just at the beginning of that. We haven't even broached that topic in large part. Since June, we've been doing through familiarization. CANDUs are us, sort of, or dummies for CANDU, whatever. Going through what is it, and describing CANDU. Now we're just getting into the ACR specific topics. And so over the next 6 to 9 months, will the NRC really be scrutinizing and asking us these very detailed technical questions, and the instrumentation and control is going to be one of the topics. But I don't think that'll be one of the critical topics. Okay, we don't believe it's one. That's not one of the 12. We're covering it, but it's not one of the 12 that we have.
Mark?
Could this design be converted to use natural uranium if you want to in the future?
In the CANDU 6, it's a garbage burner. We can do anything in there. The ACR probably has less flexibility than the CANDU 6 in terms of different fuel cycles. And so if I recall, I may be wrong, I don't think straight up you can really convert back to a natural uranium. You'd have to do something to rest the core, to the control rod, whatever, to be able to do it. But I'd really have to talk to Ben and Ruben to confirm that. I mean, I can table that question.
Yeah. Good question.
There's no heavy water right near the fuel. All the heavy water is on the outside.
Exactly. The pressure tube where the bundles lie is light water.
Just outside of those pressure tubes is still like water.
Outside the pressure tube is a gas.
The gas, but outside of that.
And outside of that is a calendaria tube, which is another little thin shell pipe, and outside of that is a moderator. Right.
How about the seismic design?
0.3G. It's designed for 0.3G. I guess there's a current debate now in the States going on about the response spectrum, and I think at the high frequency, it's a peak now that not represented the central U.S. and we don't consider that to be a problem. We design in seismic sites that are a heck of a lot worse. Turkey, Korea, China. But we're addressing it. I mean, that's something that we have to.
The problem with leaks with those many connections.
Well, if you're familiar with the CANDU 6 design, we had we call a Greylock joint, which was just bolted. Now it's welded. Okay. The feeder pipes are going to be welded. The connection from the feeder pipe to the end fitting, and I may be using jargon here that you don't understand, is now welded. We got rid of that hub where you had 4 bolts that you tighten to a certain torque with a seal that would keep it like that. Of course, depending on how things, sometimes they would leak, but
the fuel transfer machine still has to.
The fuel transfer machine comes in from the end fittings. and there's been a new bore seal closure that has been designed to mitigate and to remove the problems with the old connection where it could suffer from some leaks. So we have a new design, and I didn't bring a picture of it. I mean, you probably won't see it on the NRC website, but so we've gone a long way to mitigate. We know where our sources of leakage are of heavy water, and we've gone a long way to design them out, so to speak.
You can drop the whole reactor in from...
Yeah, that Calendria
Yeah.
ship is going to come in and drop in 700 tons and just drop in the middle, and it doesn't have to be. It could come in late in the schedule, right? That's a long-term component, right? On the contract effective date, we say go. The guys start manufacturing it. I don't know, in a month, maybe the 30th month of the schedule. I don't know when it is. I can't remember. It comes in and they drop it in, tighten it up. Away you go.
Ibrahim?
Yeah, don't have like enrichment plants in Canada. Like, what do you think? Are you going to be importing enriched uranium?
Discussions are underway with various fuel suppliers, such as chemical, and then that's all I can say.
But you aren't building an enrichment plant?
No.
And what about the containment of that? Is the problem is gone since you have like...
If you look at all the heavy water that was in the CANDU 6, I forget the ratio, like 2/3 of it was in the reactor cooling system. Okay, and most of the leakage came out of that area. We removed that, so now much less heavy water. We've attempted to design out all the moderator side leakages, so the tritium has been significantly reduced. Has it disappeared? No.
But can people go in without plastic suits, or we still need plastic suits?
Oh, and the reactor coolant side now, you can go in there and without plastics. Moderator side, no. We have in one of those silos, you have a moderator room. That is still now enclosed with its appropriate ventilation, and that would have to have plastics. But now it's a self-contained area. I mean, you're probably you're familiar with the CANDU being.
Oh, okay, because I know people used to have to go in with plastic.
Yeah. Now we don't. The reactor coolant slight water soak.
Oh,
Makes life a bit simpler.
Okay. Mahfoud?
Will we replace heavy water during operation? No.
So the 60-year lifetime comes with a 60-year supply of heavy water. It's part of the cost, right? You know, does the utility have to go back and buy more water? They lose some. Is it reprocessed?
Well, we have heavy water auxiliary systems that purify the heavy water, that recover the heavy water. There's dryers that take the heavy water vapor out and.
The number on the cost of heavy water that I recall, which is at least a decade or two old, is $100 a pound. Is that a good number today, or it has to be a lot cheaper?
No, it's cheap. I'm thinking metric, and
$100.
the number comes 500 per kilogram, but I may be wrong. I mean, I can get that number for you.
That's $200 a pound.
Yeah, 250 per pound or per kilogram? Yeah, well, I said 500 per kilogram. Well, that's a kilogram is 2.2. So. Yeah.
Okay. Yeah. Any other questions or comments for Mike? Okay, I do see a few new faces in the audience, and you may not be aware that we do have refreshments downstairs, and everyone is invited. But before we adjourn for refreshments, let's express our appreciation again to Mike. Thank you. Thank you.